This video, we're going to go through another type of strategy we can use to evaluate integrals. This one is called integration using trig substitution. Now, don't be misled to think that it's going to involve, when you look at it, you'll see trigonometry and they say, oh, so I'll use trig substitution. It's just the opposite. It's when you've got situations where there's no trig ratios in the question, but we are going to introduce trig ratios into the question, which is why it's really important that the last section on using trig identities to evaluating integrals is something that hopefully you've gained some insight into, because you're going to have to use that as we do most of these questions. I think one of the issues that students run into with anything involving these trig integrals is what really magnifies itself now is those students that do not know their identities. And they're just kind of fumbling over, looking at a page, trying to figure, well, maybe I'll do this, maybe I'll do that. And they don't have a good working knowledge of trig identities. And that really manifests itself now in these questions. And again, there's nothing anybody can do until those identities become ingrained in your head. It's probably more to your benefit to go back to the pre-calc 12A section on trig identities and just do more proofs and get better and better at those trig identities. Okay, so this method, it's basically used when you see something like this. This is kind of the pattern of Pythagoras' theorem. You could have x squared minus a squared, x squared plus a squared. So a is a number, so this could be like x squared minus 9, x squared plus 25, 25 minus x squared. Usually works best if the number here is a perfect square. Doesn't have to be, though. It can get a little messy if it's not. And these square roots are, again, the easiest ones, but it'll work for anything that basically suits this pattern that you see down here. And you're going to see through the examples that I do here that when you can throw trig substitution out as an option. And then there's certain questions you might be able to do them by trig substitution, and maybe somebody else did it by, we're going to learn another method called partial fractions, and they both work. So that can often happen as well. Well, first thing we're going to do is look at how do we represent these types of expressions on right angle triangles. And we've done this before back in, I can't remember where it was, but somewhere we talked about this before. So I'm going to refresh your memory on how to represent right angle triangles to use right angle triangles to represent algebraic expressions. So if I look at this one and I see the square root of 9 minus x squared, well, in order for me to get that measurement on one of the sides, if you see a subtraction in here, you know that it's the hypotenuse subtract the other side squared. That's how you get a missing side. So when I see the 9 first, and then minus this, that tells me I'm going to put a 3 up here. And you may be saying, 3, why are you putting 3? You'll see in a second. So I'm going to put a 3 on this side. You've got your right angle down here. You get to now pick either of these two sides, makes no difference, your choice, and you're going to put an x on that side. So if you had a triangle that had these two sides, and then I said, okay, use Pythagoras' theorem to figure out the missing side, it would be the hypotenuse squared, subtract the other side squared, so the hypotenuse squared would be 9, subtract the other side squared would be x squared. Now you can see what I'm trying to do. I'm trying to model this pattern on my third side. So my third side here by Pythagoras' theorem is going to be that squared, take away that squared, and then take the square root of it. Now then, what we usually do is pick one of the angles. As I said, either one makes no difference. Now the problem will be if I pick one angle and label it as theta, student B picks this other angle and labels it as angle theta. As we're working through our integral, it may look a little different. At the end, they'll turn out the same. But if you choose the angle other than the one I do, your integral is going to have different trig ratios in it. But as I said, it will all work itself out in the end and we'll get the same final answer. So as I said, it doesn't matter which one you pick here. So if I was saying, so what is this? How would you write this angle. There's actually 6 different ways you could represent that angle. The way you write or represent angles is using what are called inverse trig ratios. So if I wanted to get theta, I could say the easiest would be to use these two sides because you don't get into that messy radical. So I would look at this and say, well, the easiest way to represent angle theta would be to say that it is, because if you look at this diagram, I think you would agree that the sine of angle theta is x over 3. Well, if I want to get what theta is, you take the inverse sine of that relationship. The inverse sine of x over 3 is equal to theta. If you translate this to basically the way we would say it, this is, so inverse sine of x over 3 is telling you angle theta, so theta is an angle whose sine ratio is x over 3. So if student B had said, as I said when I did it, there's actually 6 different ways you could write this because every angle has 6 trig ratios, your 3 primaries and your 3 reciprocals. So let's say student B had said inverse secant of 3 over the square root of 9 minus x squared is also equal to theta. You look and say, is that also right? This is saying angle theta is an angle whose secant ratio is 3 over the square root of 9 minus x squared. The secant is hypotenuse over adjacent. Hypotenuse over adjacent. So yeah, that would also work. So you kind of get the idea of what I'm saying here is I could have said inverse cosecant 3 over x would also be theta. Inverse tan of x over this side would also be theta. Pick any of your 6 trig ratios. Now, traditionally, what we're going to do as we get working using this thinking to do integration with trig substitution, generally, we're going to pick out the easiest possible ratio we can find on the diagram. So we would use these 2 sides. But again, it's not wrong if somebody uses these 2 or these 2. It's really up to you. It's going to be your choice. And once I get this in the context of the integral, hopefully you'll understand what I mean by it's up to you and your choice. Okay, so let's look at the big thing right now is learning how to set up these triangles. So I looked at this triangle, and I wanted to set up this triangle so that it would have these 2 sides, this radical as one of the sides. Notice the difference this time you see addition. Well, that means that neither of these sides are the hypotenuse. These must be the 2 legs, because to get the hypotenuse, you square one side, you square the other side, you add them together, and then you take the square root of it. So I can tell by looking at this that this is the hypotenuse, which means I would want my 2 sides to be 5x to the third. Now the reason you want it to be 5x to the third is because when you square it to get your hypotenuse, you want to get this 25x to the sixth. You want your other side to be 3, because now if you use Pythagoras' theorem to get your third side will be this squared, 25x to the sixth, plus your other leg squared, which would be 9, and then you would take the square root of it. So that would be setting up a right angle triangle that has this messy radical as one of your 3 sides. And then you would pick an angle here, and now I can do a bunch of different things. So let's suppose I wanted to say, well, what is angle theta? Probably these 2 sides would be your best bet on this one. I could say inverse tangent of 5x cubed over 3 would be one representation of theta. And as I said, there's 5 others I could use. I could use cosine would be these 2 sides. Sine would be these 2 sides. You could do reciprocal ratios. If you wanted the variable on the bottom, you could say inverse cotan of that over that is equal to theta. So you can pick any of your 6 trig ratios, and that would be the inverse trig function that would describe the angle theta. Okay, so hopefully you see how you set up these triangles. So I'm going to move now right into how this skill that I've showed you here is going to help you evaluate intervals. All right, so I come across this interval, and right away I look at the bottom and I say, hey, that kind of looks like the pattern of Pythagoras' theorem. I've got this perfect square minus another perfect square, and I'm going to set up a triangle to represent this as one of the sides. I'm going to draw the triangle. That's how I start these. A right triangle. Because it's 9 minus x squared, I'm going to make the hypotenuse 3, one of the legs x. That will make this side 9 minus x squared. All right, so here now is where it turns into what we call trig substitution. We are going to recreate this integral involving not x's anymore. It's going to involve thetas, angles. Well, let's start by, I need something to put in there for dx. So here's what you're going to want to do to get a substitution for dx. You're going to try and find the easiest possible trig ratio you can on this diagram. So if I look at this one, I want to use these two sides. The trig ratio that would be the easiest for that would be the sine of theta. So the sine of angle theta would be equal to the opposite over the hypotenuse. Now, if I want to generate a dx, well, the only way you're going to get a dx is by taking the derivative. Sometimes students like to rearrange this first and say, okay, I've got 3 sine theta equals x. And now I just differentiate both sides of this equation. So the derivative of sine theta is 3 cos theta. Now the derivative of theta is d theta over, I'm differentiating with respect to the letter x, so think of like implicit differentiation. So you take the derivative of this variable. We did it often when it was a y, but here in this case it's a theta. So 3 cosine u, the derivative of this variable with respect to the letter x is d theta over dx. The derivative of the letter x is just a 1. Now I want to get what dx equals. So I just multiply both sides by dx. And much like just regular substitution, we'll usually skip this step as we get going, and we'll just automatically put the dx over here. But that's the reason why it's ending up over here. You're getting a d theta dx, you multiply both sides by dx, and that moves that to there. So I'm going to replace dx up here in the original question. Eventually, I'm going to put this trig expression in there instead of that. Now I need a trig expression for the square root of 9 minus x squared. Okay, so you're going to get a trig ratio that involves that side. And then you want to make sure that you set it up so that it only involves that side and a constant. So you don't want to use these two sides, because then you're going to have a variable, and then another variable in your ratio, and that's not going to help you when you go to rearrange this, because it's going to generate an extra x variable that I don't have anything there to substitute for. So the easiest thing to do here is set up this ratio, cos theta is equal to adjacent over the hypotenuse. Multiply both sides by 3. And now you can see that I have 3 cos theta that is equal to the square root of 9 minus x squared. So I'm going to go up here, I'm going to replace the square root of 9 minus x squared with that expression. I'm going to replace dx with that expression, and we're going to recreate this interval and see what it looks like involving thetas. Okay, so my new integral, colors here, my new integral. So instead of dx, if you look at the numerator is dx, I'm going to replace this dx with what it says dx is equal to, this, 3 cosine theta d theta. And of course, anytime you integrate thetas, you need a d theta. One thing you need to keep in mind here as well, I noticed some of you on your last assignment, you're mixing, you can't have multiple variables in one integral. I mean, until you get into your second and third year of calculus at university where they get into what are called double and triple integrals. That's not what we're into. We're only into single variable integration. I can't have x's in this integral with thetas. So as soon as I see d theta, I don't want anything other than thetas in this question now. I'm going to replace the denominator, square root 9 minus x squared, with this expression, 3 cos theta. Well, this one works extremely well, because if you look at that expression, look what happens. That completely wipes out the denominator, and all we're left with is this nice basic integral. So basically, this is just a 1 d theta. Now, your variable in this question is theta. So if you take the integral of the number 1 with respect to the variable theta, if this was a dx, your answer would be x. If it was dy, your answer would be y. Your integral, your variable, is d theta. Therefore, the integral of d theta is theta. Now, this is why you go up to your triangle. Now, this is where really there could be 6 different answers students could come up with here. Usually, most people are inclined to pick the easiest one. So I'm going to go with, go up to that triangle, and I'm going to use these two sides. So opposite over hypotenuse, you can even pick it out of here. If sine of theta is x over 3, inverse sine of x over 3 has got to be equal to theta. So I'm going to use that ratio. Oh, don't forget our plus c. These are indefinite. So it's going to be the inverse sine of theta. Sorry, not theta. Theta is equal to the inverse sine of x over 3 plus c. You say, what? What do you mean? Why is it inverse sine? Go up to your triangle. Look at angle theta. Angle theta, if I take the sine of it, is x over 3. So that means the inverse sine of x over 3 is equal to theta. Theta is an angle whose sine ratio is that over that. Somebody else might have written it as inverse cosine of this over this. They would also be right. Inverse tan of this over this. They would also be right. And that's where sometimes answer keys can be deceiving, because they might have picked a different representation for theta at the end than you did. Doesn't mean your answer is wrong. So just because, as I mentioned earlier in a video, that if your answer doesn't look the same as the one provided, there's no guarantee that you haven't actually still done it right and just picked out a different trig ratio as you're working your way down through. But there's an example where your trig substitution took an integral that we couldn't do, right? This wasn't chain rule. It wasn't directly one of my inverse trig function rules. So I was kind of stuck, but by doing this substitution and recreating the integral in terms of theta rather than x's, it made the integral much, much easier to evaluate. All right, so I've got a few more examples where I'm going to use this strategy, and that'll hopefully get you pointed in the right direction on how this works. So remember, this is called trig substitution. Okay, so this one's got your trig side here, but it's also got this extra x, which is fine. We'll just kind of deal with all of that as we need to. So I have to get a substitution for everything in this integral. Let's see what we get. So first thing you always do is make your triangle. Make your triangle. Looking at this, this is going to have to be the hypotenuse because I see subtract here, so that's x. One of your other sides is going to have to be 4, because then this side will be the hypotenuse squared minus the other side squared. Take the square root of it. Label one of your angles theta. Now, let's start recreating some things here. Let's start with, let's just get something for x. So the easiest thing to do to get just an x on the go with a trig ratio is use these two sides right here. So I'm going to go with, I've got two options here. I can go with sine of theta is 4 over x. But here's what I'll tell you from experience. It's always easier, I shouldn't say always, but the majority of the time it's easier if your unknown, your variable, is in the numerator. So rather than going sine of theta is 4 over x, I'm going to go cosecant of theta is x over 4. And the reason I'm doing that is because I want the x here, and I'll show you why. Because what I want to do now is get a substitution for x. Well, all I got to do is multiply both sides by 4. If student B had wrote it this way, sine of theta is equal to x over 4, sorry, 4 over x, Right? So if student B had said, I wrote it this way instead, not wrong, that's okay. But now when they go to rearrange for x, they got to multiply both sides by x. Then they got to divide by sine of theta. They get x is 4 over sine of theta. So they're going to have to substitute this fraction in for x versus the way I have it set up. So I'm going to get rid of this stuff. If you do it the other way, you're not going to put a fraction in there. Oops. You're going to just substitute that trig expression. So all I would have to do is put 4 cosecant of theta in there where there's an x, not a fraction. So that's kind of the advantage to putting your unknown in the numerator. And you can always say, well, I can't switch that. Yeah, you can. All you do if you pick side and the x is in the bottom, pick the reciprocal ratio. That flips the ratio over and work your way to get that variable up there. Using this, that should allow us to also get dx. So dx is just simply the derivative of x. So the derivative of this would be negative 4 cosecant theta cotangent theta. Now remember, it would be d theta over dx, and then we would just move the dx to the other side. So dx is going to become this expression. All I did is took the derivative of the left side and the right side. That takes care of the dx. So I've got this one covered. I've got x covered. I'm going to put this in there instead of x. I'm going to put this in there instead of dx. Now I need something to put in there for that. So again, go back to your triangle, and you want to use that side and the constant. So you want to use these two sides. And like I did in the last one, set up a ratio that puts the variable part in the numerator. I could go tan, which would be that over that, but then the variable is going to be in the bottom. So to rearrange it is going to be a little bit more difficult. So rather than using tangent, I would suggest you use cotangent this time. All right, so cotangent of theta is this side, the adjacent, over 4. So if you just rearrange that, well then 4 cotan theta is going to go in there instead of the square root of x squared minus 16. Okay, so I've got, I should highlight them. That is one part of my original question. So this is going in its place. I've got dx in the original. This is going in its place. And I had an x. So this is going in its place. So I'm just going to go up there and substitute. That's why they call it trig substitution. I'm going to substitute this for x, this where the dx is, and this where the square root of x squared minus 16 is, and see what this new integral looks like. And hopefully it's something that we can navigate our way through. All right, so the original question was, I can remember here now, it was the integral of dx over x square root x squared minus 16. So the new integral with thetas instead of x's is going to be this. So dx is this, negative 4 cosecant theta cotangent theta d theta. The letter x is 4 cosecant theta. And this is 4 cotan theta. All right, now you're getting spoiled here because you're thinking, wow, this works wonderful. They don't always work this nice. You'll see a couple of examples here after I let you get the hang of how this works. But look what happened again here. I mean, it worked beautifully. This crossed this out. Let's say this 4 crossed this 4 out. Cotan theta, they're all multiplied together, so you're allowed to cancel out these factors. All that's left here, you got your negative in the numerator, everything else is gone, and you got a 4 in the bottom. So this new question has turned out to be this, negative 1/4 the integral of d theta. Well, it doesn't get any easier than that. The integral of d theta, whoops, so negative 1/4 theta plus c. And then you go to your triangle and say, well, what would be a trig ratio I could use to represent theta? Well, why don't we go here? Cosecant theta is x over 4. So inverse cosecant of x over 4 has to be theta. And remember, there's 5 other ways students could write what they think theta is equal to. I've just picked out what I think is the easiest one. And there you have it. As I said, we're getting a little spoiled. They don't always work that nicely, but that's just 2 good examples to kind of get you going in the right direction. Now, one thing to watch for students, they see this, and after a couple examples, students usually do kind of gravitate to this one because it's very structured and they like this. The problem with it is they'll sometimes overuse it. What I mean by that, I don't think I have an example, but let's just take this for an example. If I had the integral of, I don't know, 3x over the square root of 9 minus x squared. I could, I'll put my dx here. This would absolutely work with trig substitution. Guess what? It's also just a chain rule because it's the integral of 9 minus x squared to the negative 1/2. Put your x there, pull your 3 out to the front, and you've got u to a power. The only thing missing is du. So you put your -2 here, put your -2 here, and then you've got u to some exponent multiplied by du. That right there is chain rule. So to do that, you add 1 to the exponent, which would take you to a half. Divide by that new exponent, which means multiply by 2. So this is going to become basically just -3, 9 minus x squared to the 1/2 plus c. If student B did that with trig substitution, it's going to look very different, and it's going to take probably quite a bit more work. I'm not going to go through it all, but you can see that certainly models that pattern of trig substitution that I alluded to earlier. Just don't fall in love with it where you use it every single time you see that pattern. Look for ways that might be a little bit quicker. Okay, so for example, in this one, chain rule would have been far quicker than setting up a triangle and doing trig substitution. Okay, let's do a couple more that aren't quite as maybe nice as that first 2 led us to believe this is going to be. So let's have a look at this one. So I see that I've seen this earlier, so we're going to set up basically the same triangle we did for that. So it's going to be 3 on this side, x on this side. This side becomes square root 9 minus x squared. Put my theta down here. This time I need something for x squared, I need something for dx, and I need something for this. So let's get a nice basic trig ratio that will allow us to get dx. I'm going to go sine of theta would be x over 3, which means 3 sine of theta is going to go in for the x. So I'm actually going to square that. This will be 3 sine theta in brackets squared when I substitute, because that's what x is, but it's x squared. To get dx, I'm going to take the derivative. So the derivative of sine is cos. Remember, it would be d theta over dx. The right side would be 1, and I'll just multiply by the dx. So that becomes dx. So there's my substitution for dx. Now I need something for this. So I'm going to use these 2 sides. You want the constant and the radical. We would go cos theta is equal to the square root of 9 minus x squared over 3. Multiply both sides by 3. So 3 cosine of theta is the same as the square root of 9 minus x squared. Okay, so there's my 3 substitutions. I'll just highlight them again like I did last time. So x squared, so there's x. I'm going to square that. There's dx, that takes care of that. And your square root of 9 minus x squared, I'm going to put that in its place. So let's rebuild the question and see what we got to deal with this time. All right, so this one was integral of x squared. Well, x is this. So it's 3 sine theta. There's x squared. Dx is this. And the square root of 9 minus x squared is 3 cos theta. All right, so let's see what I got now. This gets rid of this. This gets rid of this. That will tidy up a little bit, and we'll end up with this integral. The integral of 9, I'm going to put the 9 out in front, sine squared theta d theta. Oops. Well, one of the drawbacks of us doing our learning through this platform is that we're probably not getting the drill and practice of that regular every day, me throwing a few intervals at you to start a class, and you're kind of being left on your own to fend and try and do that on your own time and pace, which unfortunately sometimes doesn't meet up with what's required to get you up to speed on these. As soon as you see the integral of sine squared d theta based on the last video on integrals involving trig identities, you should know right away what you're going to do for this one. And I know right away I'm going to use a double angle identity. And the double angle identity says that if you have the cosine of 2 theta, it is equal to 1 minus twice the sine squared of theta. The reason I'm doing this is I want to rearrange and get a substitution for sine squared theta that involves a trig ratio to only the first power, because sine squared is not one of my differentiation rules. Now, if that was secant squared theta, I'd have no problem, because that is the derivative of tan. But sine squared theta is not the derivative of some trig function, so I've got to do some manipulating. I'm going to move this over here. Let's say 2 sine squared theta would equal 1 minus this. I'll divide everything by 2. And I've got sine squared of theta is equal to 1/2 minus cosine 2 theta over 2. If it was cos squared 2 theta, you do the exact same strategy, except you don't use this version of it. There's another version of it that says 2 cos squared of theta minus 1 also equals cos of 2 theta, and you'd rearrange that for cos squared. But as soon as you see the integral of cos squared or the integral of sine squared by itself, nothing else there, you got to immediately know that's going to involve double angle identities. And there's no, I'm telling you that's how it works. There's so I don't understand. I can't help you. You have to know that's the identity. You need to know those identities. So some people say, oh, I didn't know that. I don't know those. Well, that's why you can't do these, because you don't know your trig identities. So the issue is not integration. The issue is not knowing the prerequisite skills to be able to work at this level. So when you get to this level of integration, it's expected that you know a lot of prerequisite pre-calc skills, whether they're integral trig identities, whether they're knowing how to get common denominators, knowing how to factor. It all becomes very critical in your success in doing these integrals. Sorry for the rant. Sine squared theta d theta. So I'm going to replace sine squared theta with this. So now the question becomes, I still got that 9 up there. So the 9 stays. And I replace this with 1/2 minus cos 2 theta over 2 d theta. Now, there's a few things differently you could do here. What I'm going to do is, basically there's a common factor of 1/2 here, so I'm going to pull the 1/2 out front with the 9 and make it 9 over 2 times the integral of 1 minus cos 2 theta d theta. Right, so that would be the same thing, right? 9 times 1/2 is 9 over 2. 9 over 2 times 1 is the same thing. 9 times that would be the same as 9 over 2 times that. But it just gets all those constants kind of out of the way and tidies up your integral. So now what I'm going to suggest you do is you split this into 2 separate integrals. So 9 over 2 integral of 1 d theta minus 9 over 2 integral of cos 2 theta d theta. This is easy. The integral of d theta with a 1 in front of it is just theta. So this one is 9 over 2 times theta. Now, cos u, if you have the pattern cosine u times du, that's close to the derivative of sine u. The derivative of sine u is close to that, but it's negative cos u du. So in order for this to be one of my differentiation rules, I need to put a negative here, and I also need to put a 2 here. That will now give me negative cos u times du. Well, what you see in green wasn't there. I've added it in myself. Negative 2 means I have to put out in front 1 over negative 2. Those two would wipe each other out. So that is going to now change the coefficient in front to be a plus 9 over 4, because it's negative, negative. So plus 9 over 4. The integral of negative cos u du is sine u being in this case 2 theta, plus c. All right, now this one's a little more interesting, as you can obviously tell. So my triangle, I'm still going to go back to, where is my triangle? Way up here. I'm just going to draw it out down here again, just so I can refer to it, not have to scroll back and forth. So my triangle looks like this. I put the 3 here, the x here, square root 9 minus x squared here, and I put my theta right here. Okay, so theta, the easiest trig ratio I see would be these two, so I'm going to go 9 over 2, that would be inverse sine of x over 3. That would be a representation of just theta. Now, this is where this gets a little different. You're going to use a trig identity, because my triangle relates everything to theta, not to theta. So if I want to get something to put in there for the sine of 2 theta, that's what you use, a trig identity. The sine of 2 theta is equal to twice the sine of theta times the cosine of theta. It takes your angle 2 theta and relates it to theta, which is the angle on your diagram. So here, I'm going to go plus 9/4. I'll just put my trig identity in first. So plus 9/4. I replace sine of 2 theta with 2 sine of theta cos theta. Okay, this is no good. I can't have x's and thetas in my answer. There were no thetas in the original question, so you can't have thetas in your answer. You got to get everything back to x's. And the way you do that is you got to relate everything to your triangle. So that's why I wanted to get my angles here to be thetas. So now, sine of theta, I'm going to read off my triangle. It's x over 3. Cos of theta, I'm going to read it off my triangle. It's this side over this side. So we're going to do another substitution here. So 9 over 2 inverse sine x over 3. This is going to be 18 over 4, which is 9 over 2 if you reduce it. And now from your triangle, sine of theta is x over 3. Cosine of theta is this side over this side. Over 3. Don't forget your plus c. And then they'd probably clean that second term up a little bit if you check the answer key. So it'd be 9 over 2 inverse sine of x over 3. This is going to be, so this is a 9 here, little cross-sided, so it's really just going to be a half, all those constants. And then you'd have x onto square root 9 minus x squared plus c, which is your final answer. So that one got a little bit more complicated, but that's kind of where you're at. That's the type of math that we're expecting students that have arrived here to be able to work their way through. I have one more, I think, that I'll do for you. Yeah, this one's got a bit of an odd exponent. I picked it out on purpose because I wanted, so sometimes people look at it and say, oh my, 3 over 2, that's not, he didn't show us anything about that. But 3 over 2 just means this. It means the bottom number is the index. So it means the square root of 9 minus 16x squared cubed. So if we can figure out something to put in there for that, we're just going to cube it. That's all 3/2 means. So if you see a fraction exponent with the bottom number being a 2, it's probably just trying to hide or disguise nothing more than a trig substitution. So let's build a triangle for this integral. I would put 3 on this side, and I would put 4x on this side, because that would then make this side hypotenuse squared minus the other side squared. Got your theta down here, and now I need to recreate this. So I need a dx. To get dx, you want to build the easiest possible trig ratio you can, and then take its derivative. So I want to use these two sides. And remember, we always want the variables to be in the top. So I'm going to go sine of theta would be equal to 4x over 3. 3 sine of theta would be 4x. Take the derivative of both sides. So 3 cos theta d theta over dx, but remember we move the dx to the other side. 4x, the derivative is just 4, and then your dx will appear over here from the bottom of this one. So then I've got 3/4 cos theta d theta. That expression is going in where the dx is. So I need something now for this. So I showed you over here what it is. It's the square root of that cubed. Well, I want to get that to get my square root on the go and put it with your constant. So I would go cos of theta is equal to the square root of 9 minus 16x squared over 3. And then just multiply both sides by 3. So 3 cosine of theta would be the square root of 9 minus 16x squared. Okay, let's rebuild the question with thetas instead of x's. Switch colors. So it's basically, now the dx I know was written out beside it, but it's the same as having it in the top. So it had dx, which is 3/4 cosine theta d theta. The bottom was the square root of this, but it was cubed. So it would be 3 cos theta. That's the square root of 9 minus 16x squared, but it's cubed because it was 3/2. Now let's see what I've got here. So I've got, I don't normally like to work across this way, but just so we can see everything that's above us here, I've got 3/4. So the integral of 3/4 cos of theta d theta. The bottom's going to become 27 cosine cubed of theta. And let's clean this. So I've got 3/4 over 27. 3/4 divided by 27 is the same as 3/4 multiplied by the reciprocal, 1 over 27. 3 goes into 27 9 times, so it's really 1 over 36. So my integral is going to be the integral of 1 over 36. That takes care of the constants. I've got cos theta divided by cos cubed theta. Well, that is going to cross out one of those and take that down to squared. So I've got 1 over cos squared theta, and then I still have my d theta, which is always part of the numerator. All right, so I've arrived here. So students that have got their brain wrapped around trig identities and using them to evaluate integrals would be ecstatic at what they see here. Those of you struggling with trig identities might still be scratching your head saying, I don't know, how's this going to help me? 1 over cos squared doesn't help me, but me knowing this, I know that 1 over cos theta is equal to secant theta. So that means 1 over cos squared of theta has got to be secant squared of theta. So what? This is the derivative of tan. So if you can change this question to now 1/36, instead of 1 over cos squared, you change it to secant squared theta d theta. That's one of your differentiation rules. The derivative of tan theta is secant squared theta. So we're doing an antiderivative. So if I get this, I know its integral is tan. So 1/36 tan of theta plus c. Remember, the original question had no thetas anywhere to be found. That was our strategy of this. So we've got to get out of the thetas and back to the x's. Go to your triangle and figure out from your triangle, what are you going to put in there for tan of theta? So I go back to my triangle, look at my triangle. Tan of theta is this side over this side. Again, you say, oh, I don't like doesn't have a con. I can't control that. It told me to get tan of theta is part of my answer. So tan of theta is this over this. 4x. This one is going to be 1/36 multiplied by 4x over the square root. 9 minus 16x squared. Sorry. Got my pen stuck here. Undo that. All right, let's try that again. So it is 9 minus this 9 minus 16x squared plus c. Could reduce this a little bit. So if you looked at your answer key, it would probably take 4 over 36 and reduce it to x over 9 square root 9 minus 16x squared plus c. And that is how you use a strategy called trig substitution to evaluate intervals. So obviously you can see you've got to be able to be competent using your trig identities and your trig properties to go through that. But if you are, it works very, very nicely in some of these. Now, I picked examples that I think work fairly well. And if you can get your brain wrapped around this type of example, you'll be fine. Yeah, they can get more complicated, but just understanding how the process works will be a great step in helping you use this strategy in ones that maybe are a little bit more complicated. I will post some practice questions on trig substitution in your class notebook. I'll put them under handouts, and I'll try and find some that make sure that I have the solutions there with them. But you do have to be careful. The solutions can depend on which way you set up your triangle. If you set it up differently, your answers could look slightly different, even though you're doing things correct. So sometimes it's a little tougher here to gauge whether you're actually doing it correct or not if you just look at the answer, because as I said, there can be those discrepancies. All right, so hopefully this has helped you. We're down to one more integration technique left to do in our list, and then we bombard you with a bunch of practice questions.